Hello everyone, my name is Harrison Neves Marciano and I am the first author of the paper named as Singularity-Free Quaternions Representation to Control a UGV-UAV Formation Performing Trajectory Tracking Tasks. This paper addresses the problem of formation singularities, which may arise when one uses a Euclidean description for robot formation, in this case a unmanned ground vehicle with a unmanned aerial vehicle, and how a quaternion representation can overcome the singularity problem. Well, we are going to start this work by introducing the problem and how we intended to approach in order to solve it. We are going to give a little introduction of quaternions, explaining how it can solve the singularity issue. Then we are going to give our experimental setups, explaining the infrastructure available. Then we are going to give our quaternion characterization for this formation in comparison to two others Euclidean description for the same formation. And then we are going to give our controller for the trajectory tracking task that we are going to perform. Finally, we are going to show our experiments and the findings we had with them, finishing with the conclusion of the experiments and all the conclusions we could take from this work. The problem he addressed is the problem of the coordinated navigation of a UGV and UAV performing a trajectory tracking task with the possibility of the UAV to land over the UGV. The problem here is that most Euclidean descriptions will always have points of singularity. Points of singularity are points of the formation where one or more variables are not defined. That can be a problem because this undefinition may make this value be miscalculated and then bring instability to the system. That's why here we are going to propose a quaternion-based description for this formation where no singularity appears and there is no loss in the attainability of the formation space. Well, but why would we want a UGV-UAV formation of robots? Well, some very interesting applications can exemplify that for us. One very famous logistic problem is the last mile delivery, where it seems that most of energy and time is spent in the last mile, while it would be much more efficient if the manned vehicle stay in the main road and smaller vehicles would make these last mile deliveries. That's why it's an interesting solution is to keep the truck or the main vehicle that makes the deliveries always the main routes while the drones make this last mile. Another very interesting application is when you think about warehouses, which are indoor environments that could be completely automated, and the drones could see and take and carry and take the package and place them over the UGV that would then carry this package to the next stage of this process. This way saving time and avoiding humans to make repetitive efforts. A very interesting application when you think about exploration is the new NASA rover named as Perseverance. This rover went to Mars with a drone with him called Ingenuity. The main goal of this drone was simply to prove that it was possible to fly on Mars, but now that it has been proved, other missions can have a UGV and UAV together, where the UGV make most of the path, and when it gets to a place where it cannot go explore, the drone could fly over this region and see mountains and canyons and observe areas that before it would be impossible. And another very interesting application is when you think about fire in forests, which would be a very dangerous environment for humans, but you can arrive with a car and then you can use a drone to fly over the region, observe the fire, and helping the humans to take the best conclusions in how to attack this fire in order to solve this problem. In all of those applications, it can be seen that in many cases it is desirable for the UAV to land over the UGV. Unfortunately, this configuration represents the singularity point for most Euclidean representations, which can be a problem. In this context, quaternions can appear as a solution. Broadly speaking, quaternions are an extension of the complex numbers with the addition of the numbers j and k, which also have the property that when multiplied by themselves, they are equal to -1, and when they interact to each other, as shown in the first equation, they are also equal to -1. Using this first expression, one can derive the whole multiplicative table shown in this presentation here. Using the numbers 1, I, j, k and its negative parts, it's possible to make a group of symmetry, known as the quaternion group. The fact that quaternions make a group of symmetry show how important for mathematics this set of number is. But here we are going to use the unity quaternions, which have the property that their length is equal to 1. It's very important because the operations that use quaternions to apply rotations over vectors are multiplicative operations, and because its unity quaternion's length is equal to 1, they do not change the original vector's length, only its orientation. The way unity quaternions are used to represent 3D rotations is such that when you consider a vector that represents a 3D body orientation, you can place its coordinates in the imaginary part of a quaternion and you multiply it by the unity quaternion. But this multiplication is made twice, in the left by the original quaternion and in the right by its conjugated form. And you can repeat this process over and over again in order to make other rotations. A quaternion can be represented with a real part and an imaginary part, but this imaginary part is actually a vectorial part because it's composed by 3 elements. That's why it's also called vectorial part. Its conjugated form is given by its real part minus its imaginary part, as it happens with complex numbers. A unity quaternion can be represented as the cosine of theta over 2 plus sine of theta over 2 times a normalized quaternion that represents the x of rotation that this quaternion applies, and theta represents the angle of the rotation applied. Unity quaternions represents a 4-dimensional Unitarian sphere, meaning that in 3D space it makes a double covering of any ordinary rotation. It means that any possible orientation of a body in a 3D space will have 2 quaternions to represent it, meaning that it's possible to make a continuous and smooth transition between any orientation with no discontinuity, as it happens with Euclidean representations. Besides, for robot formations, there will be no undefined value for any attainable configuration of this formation. Talking now a bit about our experimental setups, we had a Pioneer 3 as our UGV and the Bebop 2 as our UAV, as well as the OptiTrack system for motion capture. The OptiTrack is functional mostly for indoor applications. Still, the main goal of this work was to validate our quaternion-based formation as well as our quaternion-based controller. As long as they have been validated, they could be applied to any other application with similar robots, as long as a functional sensing system is used. For the Bebop 2, it has been made a simplified dynamic model in order to improve its controller, as it is going to be explained ahead. Now, for this model and the parameters estimated, it has been done in a previous work also presented to Equus. The overall setup then is composed by 2 computers, a Windows desktop used to run the OptiTrack system, and the MATLAB script where the controller is written. Also, there is a Linux notebook used to run the ROS nodes necessary to make the computer's robot communication. The OptiTrack system possesses 8 cameras, and there is also a safety joystick that could overcome the controller's command if necessary. But what are the Euclidean descriptions that we are going to compare our Quartarian description with? The first one is the one presented here. Note that in this case, when the bebop hovers over the Pioneer, the value of beta is going to be 9 degrees. When it happens, the cosine of 9 degrees is 0, and it makes the value of alpha meaningless, meaning that it's up to the controller to define its value, and it becomes undefined, what represents a singularity, what's not desirable. Now, in this case, it can be observed that when the bebop hovers over the Pioneer, there will be no singularity. On the other hand, the sum of alpha and beta has to be inferior to 9 degrees. It means that even though there is no singularity for the moment of landing, it's made with a huge cost to the formation space. Now we are going to describe the quaternion-based description used in this work. Here we consider a cluster that contains all the important information of the formation. We consider that the cluster position is the same of the Pioneer. Besides, the straight line linking both robots has its orientation given by the quaternion QC, and the distance between both robots is also of interest. For this characterization, the inverse kinematic transformation will not have any undefined value for any attainable configuration of this formation, meaning that there will be no singularity. Now we are going to discuss the quaternion-based controller for the trajectory tracking task. The first step is to define our inverse Jacobian. This Jacobian is derived from the inverse kinematic relations described before, and it converts from the cluster space to the word frame. And despite it not being square, its rank is equal to the degrees of freedom of the physical system, meaning that it has a full rank. Those are the equations used to compute the inverse Jacobian. Once it has been computed, it's necessary to calculate the velocities references using the control laws. These references are calculated in the cluster space, and then they are converted to the word frame by the inverse Jacobian. With the references in the word frame, they are then converted to the robot references using the inverse kinematic matrix of each one. The bebop orientation does not affect the Jacobian, therefore it has no effect on the singularity issue. That's why, for simplicity, we have chosen that its orientation would follow the Pioneer orientation. So far, all robots have been considered as virtual points with no mass. This works well for the Pioneer, but performs poorly for the bebop. In order to fix that, it was considered a dynamic compensation modulus, as mentioned before, in order to consider the bebop dynamic behavior. The whole control system is here presented. Finally, for the first experiment, it was decided that the bebop would hover over the Pioneer throughout the whole trajectory following task. In this case, the desired quaternion cluster would be a constant. The video of this experiment follows now. Those are the results of this experiment. Here you see how the cluster followed the desired trajectory, and here you see how it follows its desired orientation. By those graphs you see that the experiment was well succeeded because its trajectory following error was smaller than 10 centimeters, and the cluster arrived to its desired value. It's important to note that the error quaternion equals to 1 and 0 in its imaginary part means that no rotation action is necessary, meaning that there is no error. And throughout the whole experiment, no undefined value was found, meaning that there has been no singularity. Now, for this second experiment, it was decided that the bebop would hover in front of the pioneer for the first 60 seconds. After, it would change its position and hover above the pioneer for the rest of the experiment. In this way, we want to demonstrate that there is no restriction to the space formation using the quaternion description. The video of this experiment follows now. Those are the results of this experiment. Here you see how the cluster followed the desired trajectory, and here you see how the cluster orientation followed its desired value. With those results, we can see that this experiment was well succeeded. Because this experiment uses a wider area, the maximum velocity of the bebop was reduced to 40%. It reduced its capability of decrease errors, but still the cluster was capable to follow the desired trajectory. About its orientation, there has been 2 transients during this experiment. Still, the controller was capable to bring its error to 0. No variable has been undefined during this experiment, meaning that there has been no singularity. All this has been done with no loss in the space representation of these formations, as it can happen with some Euclidean descriptions. As a conclusion, you can see that the quaternion-based description was capable to perform the trajectory tracking task with no singularities and with no loss in the formation space of the robots. As future works, we intend to use dual quaternions in order to introduce translation to this description. Besides, we want to include the UAV orientation to the Jacobian. That's all. Thank you all for listening.